Hi, everybody. This is Dr. Allaire from the University of Houston downtown. And in this video, we're going to be breaking down quiz number 5, which focuses on Science Teaching Competencies 9 and 10. Competencies 9 and 10 are the second set of competencies that get into the physical sciences. Like our previous quiz, you'll notice that this quiz had 10 questions on it because there's just so much content wrapped up in these competencies. It was impossible to limit it to 5 questions. So let's get into this quiz. Okay, so here we are once again in Socrative looking at our first question. Our first question has to do with circuits. And so here we had 4 diagrams of circuits, circuit A, B, C, and D. Each of these circuits contains a battery, a bulb, and a switch, which is currently in the off position. The question asks which circuit shown will produce light when the switch is closed. And so looking at this, you have to remember that in order for the circuit to work, everything needs to be connected. And there's only one diagram here in which everything is connected in the proper way, and that's going to be diagram B. The battery is connected with wires on both ends, the bulb is connected with wires on both ends, and the switch is connected with wires on both ends. All of the other diagrams have something wrong with them. So for instance, in diagram A, we can see that the bulb is not connected on both ends. In diagram C, we can see that we have 2 wires coming out of the same side of the battery, a wire missing from one side, connecting one side of the battery to the bulb. In the other diagram, we have a wire missing connecting the switch to the battery. So again, out of all of these diagrams, diagram B is the only one that shows a correct circuit with all of the parts connected properly so that when that switch is closed, the light bulb will light up. Question number 2, we have a picture that shows how a light ray behaves when with two different types of materials. So here's our light ray and we can see when it hits material 1, and it doesn't matter what material that is, hits material 1, it is bent, and then bends again as it's coming out of that material. It hits material 2 and bounces off of it. So which answer here best describes the behavior of the light ray as it encounters these 2 materials? And the correct answer, again, is going to be A. When it hits material 1, the light ray is refracted. So when we're talking about refraction, and that's a really, that's a good definition to go over. So refraction is the bending of light as it passes through a material that is a different density. So you've probably seen refraction in action. You like that? You've probably seen refraction in a couple of different ways. Number one is if you've ever seen a rainbow, particularly if you have sprayed a sprinkler in your yard, or maybe after a rainstorm, you've seen a rainbow up in the sky. And so that is a refraction in action, because what's happening is that light is passing through those water droplets. And because water is more dense than air, the light is bent. And since it's hitting multiple droplets and it keeps getting bent and bent and bent, eventually that light is refracted to the point where it is broken. And it gets broken into the component colors of the visible spectrum: red, orange, yellow, green, blue, indigo, and violet. But it doesn't have to be that extreme. Maybe you've had a glass of water and you've put a straw into it, and you might notice that the straw appears to be bent. And that's also refraction in action. Again, water is more dense than light. So when the light ray hits the water, it is bent slightly and slows down, and therefore the straw appears to be bent. It appears to be at a different angle than it really is. And that's what we see happening here in our diagram. When the light hits material number 1, you'll notice that it is bent. If it was able to just pass straight through, if this material was the same density as the air around it, we would just see the arrow going straight through, but we don't see that. We see that the arrow is very clear, the light is very clearly bent as it hits the material and then bends again to go back in sort of the original direction as it leaves that material. Now, what about material 2? This is going to be an example of reflection. Reflection is when light, in this case, hits an object and bounces off of it with about the same amount of energy. So let's go ahead and write that definition down also. Reflection is light hitting an object or material and bouncing off of it with about the same amount of energy. So we see this every day when you are looking in the mirror. And so light hits you, it bounces off of you, it hits the mirror reflects that light with about the same amount of energy, and it goes into our eyes, so we're able to see how handsome and beautiful we look as we're getting ready for class and work in the morning. So out of all of these answers, again, answer letter A is going to be the only one that is correct. The light is not being scattered in all directions in material 1. Material 2, the light is not being refracted. Material 1, the light ray is not being absorbed, and while it is being reflected, again, it's not being absorbed. And in letter D, the light is, if it was transmitted, that would be like the example I showed you before, where the light was passing straight through. This would be like a window. Okay, the windshield of your car, the windows of your car, the windows of your house, light is being transmitted. It is not being bent, it is not being scattered or anything like that. And that's a good thing. We want to be able to see out of the windows of our houses. We want to be able to see through the windows of our cars, the windshields and the windows of our cars. And so just imagine how difficult it would be to drive if that light was being blocked or bent or absorbed. We would not be able to see, or we would have a lot more difficulty seeing through the windshield and the windows, especially if they were on our car, if that was the case. Number 3, you notice that after you walk across a room, you feel a spark when you touch the doorknob. What energy transformation must have taken place? So this is very simply mechanical to electrical. All right, the conservation of energy says, the law of conservation of energy says that energy can neither be created nor destroyed. So it has to come from someplace and it has to go to someplace. It can't just appear out of nowhere and then disappear. So what happens is that energy can be transformed. So we have all of these different forms of energy: thermal energy, electromagnetic energy, mechanical energy, sound energy, light energy, chemical energy, mechanical energy. So in this case, we have a transformation from mechanical, which is movement. So it's the movement, your feet rubbing along a carpet, your pant legs swishing back and forth, to electrical. So as your feet are rubbing along the carpet, as your pant legs are swishing back and forth, you're building up static electricity. And the same thing if you were to rub a balloon on your shirt. And so when you reach for the doorknob, you feel a spark, and that is going to be that transformation from mechanical to electrical. Question number 4, we have a diagram of a partial food web. Now we say this is partial because obviously it does not include every single organism that we can find in this particular forest. But you can see here that we have willows and spruces, our plants in our food web. These are our producers. And then we have various consumers. We have organisms like the snowshoe hare and caterpillars, which are primary or first level consumers. That means that they are consumers that eat plants. And then we have other organisms like shrews, red-tailed hawks, a lynx, and a red fox, and these are secondary or second-level consumers. That means that they eat other animals in order to get their energy. So we have a partial food web. Which of these lists contain only animals that receive energy transferred directly from consumers in this food web? So as I mentioned, our snowshoe hare and our caterpillars, they're consumers, but they get their energy by eating producers. So any of these lists in our answers that contain the name snowshoe hare or shrew are going to be incorrect. And so when we look at our answers here, we see that we have that the only one that does not contain snowshoe hare, okay, so B has snowshoe hare and caterpillars, so that's going to be out. C has snowshoe hares and caterpillars, and D has snowshoe hares and shrews. So again, according to our food web, snowshoe hares and caterpillars, while they are consumers, they eat producers. We're looking for animals that receive energy transferred directly from consumers. So that means animals that eat other animals. And the only answer here that satisfies that criteria is going to be A. And that's because neither snowshoe hare nor caterpillar appears in this list. Number 5, we're halfway through. We have a photo of a student observing a plant through a microscope. So here is a microscope. We have a light source on the bottom. It's shining light up through the slide or the specimen. We have our various lenses for zooming in and out of our microscope. And the light goes up to the eyepiece where this student is able to look at it. So which statement describes the behavior of the light in the microscope? Is it A, light refracts through the lens of the microscope? B, light travels through the microscope lens without changing direction? C, moving in straight lines causes light to increase in brightness? Or D, moving in straight lines keeps light from reflecting? And so we can do some process of elimination here. Because moving in straight lines keeps light from reflecting, that really doesn't make any sense. Moving in straight lines causes light to increase in brightness. That doesn't make any sense either. Neither of those are really related to anything and don't have anything to do really with this particular microscope. So we're left with a 50-50 choice. Either A, light refracts through the lens of the microscope, or B, light travels through the microscope lens without changing direction. If we look at the diagram here, we can see that there is in fact a bend here in the light piece hitting the lenses. And so light is going to be changing directions. And so that means that letter B is going to be out. We can cross this out. Sorry for my bad crossing out, which means that the only correct answer in this case is going to be letter A, that light refracts through the lens of the microscope. Number 6, the state of matter that has the greatest amount of energy. Well, we're all familiar at this point with solids, liquids, and gases. And so all of those states of matter have different amounts of energy. Solids are packed, have molecules packed very, very close together, and they jiggle a little bit. They jiggle a little bit back and forth. Liquids are spread out a little bit, and therefore it allows them to move around. So again, solids are close together, and what this does is it gives solids a definite shape and a definite volume, and that's because solids have are compared to the other states of matter, have a pretty low amount of energy. As we give the solid more energy, those particles start to move faster and they start to separate, and then they're able to move around each other. And so what this allows liquids to do is it allows them to flow. And this is why liquids have no definite shape, but they still have a definite volume, okay? Because even though now those particles can move around each other and they're moving faster than they were before, they still keep their volume. They're still held fairly close together. Now, if we were to give them even more energy, those particles will start moving even faster, and eventually they will break apart. And they're just moving around all over the place. They're bouncing off of you, they're bouncing off of each other, they're bouncing off of me, they're going all over the place. And that's because gases out of our 3 states of matter have the most energy. And what that means for a gas in terms of its shape and volume is that, remember, a solid had a definite shape and a definite volume. A liquid has a definite volume, but no definite shape. A liquid will take the shape of its container. Gases have no definite shape and no definite volume. Not only will they take the shape of their container, they will expand or contract to fill up an available space. So, for instance, if you have an air freshener at home, you put that air freshener in one part of your house, eventually some other part of your home will smell like potpourri or fresh scent or whatever it is that you've plugged in, because that scent will spread out to fill the available space. At the same time, we can take gases and we can squeeze them together and put them into small containers like scuba tanks, propane tanks, aerosol cans, and things like that. And so out of these choices, again, gases have the most energy. Number 7. So solids, liquids, and gases can be changed. They can be transformed in a lot of cases. The temperature at which solids will change into liquids is known as the melting point. So just to clarify here, when we're melting something, we are adding energy into that system. So, and what we're doing is we're adding enough energy that that solid is transforming into a liquid. Now, if we were to continue to add energy, we would eventually get to a boiling point, depending on what the substance is, and that's the point at which a liquid turns into a gas. So this is when we're putting energy into a system. Now, if we were to take energy out, if we had a gas, which, as we were just talking about, has the most energy of our 3 states of matter, if we were to take energy out of that gas, eventually that gas would transform. We'd get to a temperature where that gas would transform from a gas into a liquid. And that's called the condensation point. It's going to be the same temperature as the boiling point. It's just that instead of putting energy in, we are taking energy out. So using water as an example, water boils at 100 degrees Celsius. If we keep going, it's just going to be a gas. It's going to be water vapor. And so if we have water vapor, if we have a gas that's 120 degrees and we cool it down to 100 degrees, it will condense from a gas to a liquid. And you've probably seen condensation in action, not quite the same rhyme, but you know what I'm talking about here. So for instance, if you're drinking a cool glass of water on a hot and humid day, you're going to notice that the outside of the glass is wet. And that's because the temperature of the water in that glass is cold enough to pull water out of the air and cause it to condense from a gas to a liquid. This is the same reason why on some days we find dew on plants and the sidewalk and our cars in the morning, because those things have, the air has gotten cool enough for water to condense from a gas to a liquid. Now, again, if we continue to take energy out of that liquid, we will eventually get to the freezing point, which is when a liquid will transform into a solid. So, and again, that's going to be the same temperature. So the melting point for water is 0 degrees. That is also the freezing point of water. So if we continue to take energy out of water to the point where it gets to 0 degrees Celsius, it's going to transform from a liquid into a solid. When it gets below that, it stays a solid, and like an ice cube. If I take that ice cube out, that temperature starts to rise, and it transforms once again from a solid into a liquid, otherwise known as melting. Going on to number 8. We have a student who is looking at a light bulb or a light source. And so in this side of the diagram, we see that she's looking at this light source through a bent tube. And this diagram on the right, where she's looking at it through a straight tube. So through which tube, if any, will the light be seen, and why? So is it A, neither tube because both tubes absorb all the light, B, both tubes because light travels equally well through straight and curved paths, C, the bent tube only because light bounces off the sides of the tube and travels through the tube to the student's eye, or is it D, the straight tube only because the light travels in a straight line directly to the student's eye? The only correct answer here is D. Light travels in a straight line. The only time it will bend is if, as we talked about with refraction or even diffraction, which we're not getting into in this video breakdown. But with refraction and diffraction, the light is hitting an object and being bent. And so while, yes, there is the possibility that some light is getting through the bent tube, okay? So as C describes, the bent tube, because light is bouncing off the sides of the tube, travels through the tube to the student's eye. Yes, there is a distinct possibility that light will bounce off of the sides of the tube and get to that student's eye. However, between a bent tube and a straight tube, the straight tube is going to be much, much better for observing that light, and that's what makes D the more correct answer. So again, thinking about energy transformations, going back to one of our previous questions here, we have a student that's doing an evaporation investigation. We have a lot of rhyming going on in this video breakdown. And so they are investigating the how long it takes for a wet sponge, the water in a wet sponge to evaporate. Now, we're assuming, and of course we don't want to assume, but we are going to do that in this case, that the sponges are the same size, they're the same shape. The student was being careful to have the same amount of water in both sponges, okay? Maybe measuring them by weight or something like that, okay? And so we have, on the one hand, on the left side, we have a fan blowing air on the wet sponge. On the other side, we have a lamp that's on, shining a light onto the wet sponge. So which forms of energy are being compared in this student's investigation? Is it A, mechanical energy and electrical energy? Is it B, mechanical energy and thermal energy? Is it C, light energy and thermal energy? Or is it D, light energy and electrical energy? So now, even if you're not sure, we can do some process of elimination here. Again, looking at our diagram, we see that this fan is on, which means that it's in movement, it's in motion, and the energy of motion is going to be mechanical energy. So we can eliminate two of our answers, either light and thermal energy or light and electrical energy, and we're left with either A or B, mechanical energy and electrical energy. So now we can think about this, and yes, both of the light here is plugged into an electrical outlet. So yes, there is electrical energy involved, but both of these are plugged into electrical outlets, which means that both of these run on electricity, but that electrical energy is being transformed into something else. In the case of the fan, the electrical energy from the outlet is being transformed into mechanical energy, which is the movement of that fan to blow air on the sponge. In the case of the lamp, that electrical energy is being transformed into thermal energy. And so A can be eliminated because both of these appliances use electrical energy. So the most correct answer in this case is going to be B. Mechanical energy and thermal energy are being compared in this particular investigation. And number 10, this table lists ingredients of 5 different mixtures. So here we see mixture 1 has salt, hot water, and sand. Mixture 2 has sugar, hot water, and salt. Mixture 3 has iron filings and sand. Mixture 4 has pebbles, wood chips, and soil. And number 5 has powdered soap and hot water. And so in which mixtures do all of the ingredients maintain their physical state? So again, thinking about states of matter, solids, liquids, and gases, we can do some process of elimination here. We have some 3 mixtures that involve hot water. Mixture 1, mixture 2, and mixture 5. When Sand is added to hot water, as we've seen at the beach. Whether it's added to hot water or cold water, sand does not dissolve. It doesn't change its state of matter. It doesn't change from a solid to a liquid or anything like that. However, salt added to hot water will dissolve, meaning that it changes its state, its physical state from one form to another. So mixture 1 is going to be out. In mixture 2, both salt and sugar are going to dissolve in hot water. So similar to number 1, both of these items are going to be changing their physical state, and they will no longer be solids when they are mixed together. Number 5, we have hot water and powdered soap. When you do your laundry, if you use powdered soap or any kind of detergent, that detergent is changing its physical state from a solid into, in this case, a liquid, because it's being added to hot water. So 1, 2, and 5, the ingredients are not going to maintain their physical state. So therefore, any list here that contains mixtures 1, 2, or 5 is going to can be eliminated. So A says mixtures 1, 3, and 4, so we can eliminate that. B says mixtures 1, 2, and 5, the ones that we just got done talking about, so that can be eliminated. Letter C says mixtures 2 and 5. Both of those are ones that we just discussed and can be eliminated. And so therefore, the only correct answer in number 10 is going to be D, mixtures 3 and 4 only. Because out of all of these mixtures, when I mix the iron filings and the sand together, they are both solids, they will stay solids. When I mix the pebbles, the wood chips, and the soil together, even though everything's going to be all mixed up, all of them are solids, all of them will stay solids. So mixtures 3 and 4 maintain their current physical states. So that's going to do it for quiz number 5. Again, focusing on Science Teaching Competencies 9 and 10, the second set of competencies in physical science. We'll see you next time. I hope you found this video to be helpful.